Hello. It's now time to look at an example of equilibrium of an extended object. Specifically, we will learn how to use the conditions of equilibrium we discussed in the previous video to solve for unknown forces in our example. In this example, let's say you and your friend work at a construction site, and today your job is to carry a piece of lumber from one place to another. And this piece of lumber is 6 feet long, and because the mass in it is not uniformly distributed, and that's because, let's say, it's got a dense knot over here, so the center of mass of this log, rather than being right at the center, is shifted towards this end. And let me give you the specifics. So the log itself was 6 feet long, and the center of mass, let's mark it over here, is 2.4 feet from the left end. And let's say the log weighs 500 newtons. So I'll show its weight acting straight down as 500 newtons right here at the center of mass. Okay, so your friend offers to pick up this left end, holding the log by its very edge, and you have to pick it up from the other end. And the question is, how much of the weight of the log will you support and your friend support based on where you decide to pick it up? So your friend's hand is holding the log right there, so the normal force from your friend's hand on the log will be positioned at that point. Let's call that N1. And let's say you do the logical thing and pick it up at the other end, and so your normal force is going to be N2 at this end. And our job in this problem is to determine these normal forces, which is a measure of how much of the 500 Newton weight your friend carries and you carry as you move this log from place to place. Okay, so let's see how the equilibrium conditions we have learned help us solve this problem. So the first condition was sum of forces in the F direction had to be 0 for this log to be in equilibrium as we carry it. And that doesn't get me anywhere because there are no forces in the X direction. Well, just for clarity, let me say my X-axis, as usual, is horizontal, and Y-axis here is vertical. The second condition is sum of forces in the Y direction is also 0 for equilibrium, and that gives me something. So now I can add up all the forces in the Y direction. I've got N1 in the positive Y direction, so for clarity, let me say plus N1. I've got N2 in the positive direction, and I've got 500 Newton force here in the negative Y direction, and the sum of all those forces have to be 0 for this log to be in equilibrium. And if I simplify that just a little bit, I get N1 plus N2 equals 500 newtons. And that's logical. The total amount of weight supported by my friend and me as we carry this has to equal the weight of the log. That's all that condition is telling us. Well, we now have one equation and two variables, and you know we can't solve for these variables with just one equation. If we have two unknowns, we need two equations to solve for them. So the second equation comes from our new condition of equilibrium of an extended object, which was that the sum of all the torques around any point also had to be 0. So as discussed before, I can take the torque around any point, but some points will make our job easier than others, as we will see. So for starters, let me take a point right at the center of the log and see what that leads to. So that's going to be my point of determination of torque from all the forces. So I've got N1, and around the center point, N1 will have a clockwise torque. And so the torque from that force is going to be minus because of the clockwise direction. And the actual torque value is the force N1 times the distance of that force from the point of pivot that I'm using. And since I chose it right at the center of the log and the log is 6 feet long, that distance is going to be 3 feet. So N1 times 3 would be the torque from that force, and it's negative because it's clockwise. Then I got the 500 Newton force of weight that's going straight down here, and around this pivot point, this 500 Newton force is going to create a counterclockwise torque. So that would be a positive, so I'm going to add 500 newtons times the distance of this force from the pivot point. So since this overall distance from the end to the center is 3 feet, and this is 2.4 feet to the center of mass, what's remaining here is 0.6 feet. So this distance here is going to be 0.6 feet. So the lever arm for the weight is 0.6 feet. So I've got to multiply 500 by 0.6. And then I have the torque from force N2, which around the pivot here that we chose at the center is going to be a counterclockwise rotation, and counterclockwise is positive. So I have plus N2 times the lever arm, that perpendicular distance, which in this case is also 3 feet because we chose the pivot right at the center. The log is 6 feet, so from the right end it's also 3 feet distance. And the sum of all of that have to be 0 as we carry this log in equilibrium. Okay, now it's just a matter of simplification. So I've got 3 times minus 3 times N1 plus 500 times 0.6, you can check in your calculator, will be 300. And plus 3 times N2 is 0. So now I can just simplify this a little bit more. And by dividing through by 3 and then moving unknowns to one side and the knowns to the other side, this will simplify down to N1 minus N2 equals 100. You can check that on your own as an algebra exercise of simplifying that to this. And the unit of this was newtons, so just for clarity, let me add that over here. So now I got two equations, one from the sum of Fy forces and one from the sum of torques being 0. And two equations are enough to solve for two unknowns. So now I can solve for N1 and N2 and get the answers of how much weight my friend supports and how much I support. Well, I'm going to pause here for a second and not do this because solving, while it's possible to solve two equations and two unknowns, there is an easier method. So let's choose a different pivot point. Since I'm free to choose any pivot point, for now I'm going to choose my pivot point to be on the very left end right there. The reason for doing that is to make our equations simpler. And you would notice that by choosing that pivot point, the torque from N1 is going to be 0. It does not have any lever arm. It goes through the pivot. So now when I do my sum of torque conditions, let me do it here. Sum of torque equals 0. That leads to 0 torque from force N1 around this pivot, since there is no lever arm. A clockwise torque from the weight, clockwise is negative. So now I got 500 times the distance of the weight from the lever arm, which is 2.4 feet. And then I got a counterclockwise torque from N2, and counterclockwise is positive, so I got plus N2 times its lever arm, which is the entire 6 feet, its distance from the pivot, and that has to equal 0. And simplifying a little bit here, I get minus 1,200. That's what you would get when you multiply 2.4 by 500 plus 6 times N2 equals 0. So now you notice that my second equation only has one variable. So I don't need to solve two equations simultaneously to solve for N1 and N2. I can use this second equation here to solve directly for N2. And I will do that by first adding 1200 to both sides, which will give me 6N2 equals 1200. And then I can divide by 6 on both sides, and that'll give me N2 equals 200 newtons. So there we go. I've already solved for the weight that I'm going to carry of this log. Then I can use this value and use that first equation we got from sum of forces in the y direction. So by substituting N2 into that equation, I end up getting N1 plus 200 newtons equals 500 newtons. And by subtracting 200 newtons from both sides, I would get N1 equals 300 newtons. So my friend carries 300 newtons of the weight of the log, and I carry 200 newtons. Why did I get lucky? Because he offered to carry the end that was closer to the center of mass, so the weight of this dense knot was leaning more into him than it was into me. So in this slice of physics, we learned how to use conditions of equilibrium of an extended object to solve for unknown forces in various situations.